A centrifugal pump with a 40 centimeter diameter impeller pumps water at 20 degrees C. During testing at 900 RPM, the following performance data are measured. Determine the specific speed of this pump. So the performance data that we're given here is volume flow rate in thousands of liters per minute, the head in meters, and the brake horsepower in kilowatts. So we'll begin here by listing our given information. And as I said, we have test data for a centrifugal pump, and it's H and brake horsepower as a function of flow rate. We're given the pump speed at 900 RPM, the impeller diameter at 40 centimeters, and this pump is pumping water at 20 degrees C. And what we're asked to find is the specific speed. And what we'll be finding is what we called N primed S in the notes. So this is the true specific speed, fully non-dimensionalized, not the more informal one that's based on gallons per minute and head in feet. So our assumptions here, this pump is operating at steady state and an incompressible fluid. So the analysis will begin just by pulling out the definition of specific speed. So it involves the speed of the pump, the volume flow rate, G, and the head. And notice that Q and H are both at the best efficiency point. So the specific speed is always calculated at the most efficient point of the pump. And we denote that Q star and H star. So Q and H have to be evaluated at the best efficiency point. Now, we don't know where that is yet. We have a whole bunch of data at different values of Q and H, so we're going to have to calculate the efficiency at each of those points and see which one is the BEP. So how do we do that? Well, the efficiency of the pump is the water horsepower divided by the brake horsepower. And the water horsepower is rho GHQ, and the brake horsepower we've been given, that's W dot S. So we're going to calculate this for each row in that table. So here's a sample calculation at 10,000 liters per minute. So we have our density, 998. Remember, we're at 20 degrees C, and that's the density of water at 20 degrees C. G is 9.81. The head at 10,000 liters per minute is 29 meters. And then we need to be careful here to convert our liters per minute to cubic meters per second. So we divide it by 60,000. And our power, the brake horsepower, was 73 kilowatts. So we put that in here in watts. And when we do that, our efficiency will be 64.822%. So we do that for every row in the table, and we get this. So now we have this extra column here, which is the efficiency at each of these test points. And we see that our best efficiency point is at 84.8%, a flow rate of 30,000, and a head of 22. And that's what we need to know to calculate the specific speed. So we go ahead and do that. 30,000 for Q star and 22 for H star. So we substitute everything into our expression for the specific speed. So the speed of the pump, we want to put that in revolutions per second. So we need to divide our revolutions per minute by 60 to get revolutions per second. Also remembering to convert our volume flow rate to cubic meters per second. And then G and H, there's no conversions required. So that gives us a specific speed of 0.18837. So we can conclude that the specific speed of this pump is 0.188. So the usefulness of this specific speed is it's a very good guide to what type of pump we should be selecting. So we know in our application perhaps that we want a flow of 30,000 and a head of 22, and of course we want that to be at our best efficiency point. So we can calculate that based on the speed we're going to operate that pump at and the Q and the H that we want to achieve. So we want to now go looking for a pump that has a specific speed of as close to 0.188 as we can. And that will depend on the design of the pump. A purely radial flow pump, so a centrifugal pump, will have a very low specific speed, and an axial flow pump will have a high specific speed, and there's a whole transition between those. So we'll be able to select the proper pump design by calculating this specific speed.